AI is everywhere. We all know that. But for all of its incredible power, it's still pretty much a mystery. So, what if we could change that? Today, we're going to explore a new scientific theory that's trying to crack open that black box and finally, understand how deep learning actually works.
This is the big question, right? It's what keeps researchers up at night. We've built these amazing, world-changing tools, but how they really work on the inside, well, that's often a bit of a mystery. For years, deep learning has felt a lot more like alchemy than it has science. But you know what? That's starting to change.
So, the heart of the problem is this black box idea. We give it an input, say a picture of a cat, and we get an output, the word cat. But what happens in between? That's been the mystery. For the longest time, building AI has felt less like principled engineering and more like just messing around, a mix of trial, error, and a whole lot of intuition. And here's where it gets really tricky for scientists. Our old theories just can't handle it. They were designed for much simpler models. But today's neural networks are absolutely massive. They have way more parameters than there are data points to train them on. According to classical theory, they should just fail, like spectacularly. But they don't. They work incredibly well. And that huge gap between what our theories say should happen and what actually happens, that's what we need to fix. And that fix, that new approach, is really starting to come together. Instead of one single eureka moment, scientists are finding clues, all these recurring patterns and strange behaviors that all seem to be pointing towards some kind of unified theory. We're going to walk through 5 of the biggest clues they've found so far. Think of it like a detective story. We're going to look at the evidence, we'll see how simple toy models can give us some powerful intuition, we'll look at how thinking about infinite systems can actually reveal fundamental truths. We'll discover how simple, predictable math seems to pop out of total chaos. We'll see how we can finally start to tame all those knobs and dials we have to tune. And last, we'll see how totally different AIs seem to be learning the same things universally. Okay, our first clue comes from a classic strategy in science. If you can't solve the really hard version of a problem, solve a simpler one first. You know, like in physics, you don't start with a black hole, you start with something simple, like a pendulum. Those simple, solvable systems give you this deep intuition that you can then apply to more complex stuff. And it turns out we can do the exact same thing for deep learning. And check this out. This is a perfect example of what I'm talking about. We're looking at a deep linear network, which is just a toy model where we took out some of the complicated bits. The solid lines, that's what the math, the theory predicts should happen. The little dots, that's what actually happened in the experiment. They match perfectly. I mean, this is huge. It proves that in these simplified settings, we can actually build theories that make precise, verifiable predictions. So that's what happens when we make things simpler. But what if we do the opposite? Now, this is going to sound a little nuts, but our second clue comes from making things infinitely complex to find simplicity. This is another trick borrowed from physics. The ideal gas law, for example, is technically derived by assuming an infinite number of particles, but it works perfectly to describe the air in this room. Now, studying these infinite networks has revealed this fascinating split. It turns out, depending on how you set up the network right at the beginning, it can learn in one of 2 totally different ways. On the left, you have what's called rich learning, where the network really digs in and learns new features, fundamentally changing how it sees the data. But on the right, you get lazy learning, where the network pretty much stays the same and just tweaks its final output a little. This shows us that one simple setting can completely change the way a network learns. These insights from infinite models are really powerful, but what about the actual finite models we use every single day? Well, clue number 3 reveals that even in all their chaotic glory, they follow these surprisingly simple rules. You'd expect a system with billions of moving parts to be just pure chaos, right? But it turns out certain key properties follow these simple, almost elegant mathematical laws. The most famous example, you've probably heard of it, is neural scaling laws. What this chart shows is that a model's performance isn't random at all. It gets better in this beautifully predictable way as you give it more computing power, more data, or make it bigger. The fact that these lines are perfectly straight on this kind of plot, that's a massive clue. It's screaming at us that underneath all the complexity, there's a simple mathematical principle making it all happen. Here's another one that's just wild. So imagine the training process is like a ball rolling down a bumpy hill, trying to find the lowest valley. This chart measures how sharp or bumpy that hill is. And what's incredible is that no matter what kind of model you're training, that sharpness always rises to a predictable ceiling. And that ceiling is set by just one number, the learning rate. It's another powerful piece of evidence that simple rules are running the show behind the scenes. Okay, so finding these hidden rules is amazing. But what are they good for? How can we actually use them? Well, our fourth clue shows how this new understanding is helping us tame the absolute jungle of hyperparameters. You know, all those little knobs like learning rate, batch size, initialization, all the things practitioners spend so much time fiddling with. It turns out theory can help us understand exactly what each of these knobs is really doing. And this right here is where theory becomes incredibly practical. On the left, using the standard methods, the best settings change completely when your model gets bigger. You have to retune everything. But on the right, using a new method derived from theory called U-parameterization or UP, the best learning rate just stays the same no matter how big the model gets. This is a total game changer. It means you can find the perfect settings on a tiny cheap model and then confidently apply them to a massive one, saving a ridiculous amount of time and money. Being able to predict behavior like that is a huge win. But for our final clue, we're going to zoom out even further and look at something even stranger. The fact that universal ideas are starting to pop up in totally different AIs. We're talking models with different architectures, trained on different data for completely different tasks. This finding is honestly profound. What this chart is showing is that as language models get better and better, the way they represent concepts on the inside starts to look remarkably similar to the way vision models do. It suggests that as these AIs get smarter, they might be independently discovering the same fundamental way to understand the world. It's like they're finding a universal language of concepts. So what do all of these clues, the solvable models, the infinite limits, the empirical laws, the tamed hyperparameters, and these universal phenomena, what do they all add up to? Well, they're all pointing to the birth of a brand new scientific field. And the researchers behind this work, they've given it a name. They argue that this new theory will take the form of a mechanics of the learning process, and that's a direct callback to physics. So what the heck is learning mechanics? Okay, think of it like this. In classical mechanics, you've got laws like F equals ma that tell you exactly how a ball is going to fly through the air. Learning mechanics is trying to find the equivalent laws that can predict how a neural network will move through its giant space of possible settings as it learns. It's literally the physics of deep learning. Now, it's really important to distinguish this from another approach you might have heard of, mechanistic interpretability. The source material uses this fantastic analogy. Learning mechanics is the physics of AI. It's looking for those simple, universal laws that describe how the whole system behaves on average. Mechanistic interpretability, on the other hand, is the biology of AI. It's trying to reverse engineer individual circuits to understand how one specific part works. They're not fighting each other. They're totally complementary sciences. You need both. Okay, so we've got an emerging science with a really cool name, but why does any of this actually matter? What's the real-world impact of all this theory? Well, it comes down to three big things. First, scientifically, if we can understand artificial intelligence, maybe we can uncover deep principles about our own intelligence. Second, and this is happening right now, this theory is helping us build better, more efficient models with way less trial and error. And finally, and this is so critical, there's safety. You can't reliably control or govern a technology that you don't fundamentally understand. Real science is the bedrock for building safe and reliable AI. And that really brings us to the final thought here. For centuries, physics has been revealing the fundamental laws of our universe. So if AI also has a physics, a learning mechanics, it just begs the question, what fundamental truths about the very nature of learning, of representation, and even of intelligence itself are we about to discover?